Hey everyone, and welcome to another challenge Writeup video. This is pwnshop. It's a older hack the box challenge, and it was fun for two different things. First, we're going to be doing a stack pivot. So this occurs when we can ROP, but we're not given enough place to actually put our ROP payload, so we have to pivot somewhere else where we can do our ROP execution. And the second thing is they don't give us Libc. And so as part of this challenge, we had to figure out what Libc the remote server was using, and then download that so we can calculate offsets and eventually get shell. Overall, pretty fun challenge. I had a good time solving it. For the rest of the video, we're going to be playing with the binary for a little bit. We'll look at checksec. We'll see what it actually looks like. We'll jump into Ghidra. We'll just do a little bit of reversing. I'm not going to reverse the whole binary. I'm just going to point out a couple of different bugs and fun things. We're going to go over we're going to whiteboard the solution. So we're going to look at how memory looks and kind of track the stack and the execution as we do our stack pivot. And then we will look at the solve script. There's one for doing it locally. And then we're going to look at the remote solve script where we have to uncover what version of Libc the challenge binary is using. Yeah, with that, let's get started. So we're only given one file as part of this challenge, and that is file pwnshop. Just this elf, nothing else. We can see it's a elf 64-bit and it's stripped. If we do, let's jump into an Ubuntu box. Then we can run checksec. Oops. Checksec file equals pwnshop. We can see pi is enabled, NX is enabled, no canary, and partial row. So maybe we can use the got for overriding something, and pi is enabled, so if we're going to be mucking around in the main elf segment, we're going to need some info leaks. Otherwise, no canary, so we're probably going to be doing some sort of buffer overflow, and NX is enabled, so we're not going to be doing shellcode. But we can run the challenge. HTB pwnshop, what do you want to do? There's only two options. It's a pretty simple binary. We can buy, sorry we weren't selling. We can give some details, nothing happens. We can do sell, what do you wish to sell? I don't know this, how much do you want for it? Sure. We get reflected content here, which is interesting. And it says the best I can do is 1337. But yeah, let's jump over to Ghidra. Cool, and now Ghidra is open. Unfortunately, the binary is stripped, so it's not going to be the easiest to reverse, but we got lucky and we just jumped to the main function, or what looks like the main function here. But if you go through, there's usually a function that'll call another function right at the start. Let's see if we can find it. Usually it's called entry. So normally this function is already called entry, and this function right here will be main. So we can jump here. All right, so we have the main function, hack the box pwnshop. What do you want to do? We can either buy or sell. Just based off of this, we can figure out what the functions are. So if char is equal to 1, that's the buy. So we know this is our buy function. And 2 is sell, so this must be sell. There's nothing really else here. They're doing some initialization here. That's just buffering and the alarm, so we don't really care about that. So nice and simple. We only have two functions to reverse. If we look at buy, nice and simple function. It's defining a 72-byte stack variable. And it says, sorry, we're not selling. It's going to print. And then it's going to read in OX50, which is 80 in decimal. So we have a 8-byte overwrite. If we look down here at the assembly, they're not doing a leave ret. It's just a ret. So in this case, the only thing we get to overwrite is the RIP that's on the stack, which is interesting. So we can only write the RIP and nothing else. So if this was a ret to win, that'd be okay. We just jump straight to the win function, but here it's a little bit different. There is no ret to win, like there's no shell already built into this binary, so that's interesting. The other function is sell. So there's two different things we can do with this. So the first thing is, what do you wish to sell? I'm not really sure what Ghidra is doing here. It's doing this looping. I don't know what it's for, and it wasn't necessary for solving the binary, but basically it's going to read in OX1F bytes into this buffer, and that's going to ask us how much we want for it. Then it's going to read into this buffer, and then it's going to do a comparison. If it's 1337, we get to insert some more stuff, and if it's not, it's going to print out whatever we sent it with this %s. Local 28, if we follow that back, so local 28 equal to 0, 28, 28, it's just defined on the stack right here. It's only reading 8 bytes, but it's very possible that this will print be something interesting. So when we do this %s here, we could potentially use that as a info leak. So if we can fill up that buffer, maybe %s will continue printing until it hits that null byte. If we can fill up that buffer and it's aligned with something else interesting on the other side, potentially we'll get an info leak, and that will actually be our info leak. And yeah, that's pretty much the entire binary. So top level overview of what we're about to do. First, we're going to do a info leak for the main binary. Then we're going to get an info leak for Libc. and then we're going to call out to system bin shell. To do the first info leak, we're going to abuse that %s printf so that it kind of leaks contents beyond what it was supposed to leak. For leaking the libc, we're going to be doing a rot payload and a stack pivot. And to do the final system bin shell, we're again going to do a rot payload, and we're going to do another stack pivot. So starting out with the first thing, we were going to do the info leak. Do the info leak for pwnshop. And so the way we were going to do this is in one of those functions, I can't remember if it was buy or sell, there was a variable defined on the stack, and let's just call it in buff. And it was going to do read in buff for 8 bytes. After it read it in, eventually it did something along the lines of printf %s in buff. It was also setting the variable right next to in buff equal to some value. I don't know what it is, but let's just say it was 40, 80, 50, something in that realm. So what's interesting about printf %s is that it will continue printing whatever is in buff until it reaches a null byte. And so if we can set in buff to completely fill up the 8 bytes it has, it'll go, 1, 2, 3, 4, 5, 6, 7, 8. It'll start reading into the next memory address. Like, it doesn't care what it's reading. It's just going to keep reading until it reads a null byte. And because we're on a little endian system, we have to remember the bytes, like reading this way. There'll be bytes over here, and then it'll end in null bytes over here. So we're actually going to leak this address because it's going to go, these little bytes will be displayed first. So it's actually going to be like if we're writing it out like this, but in memory, it's going to be OX50, OX80, OX40, and then 0, 0, 0, 0. So because of that, as long as we give in buff 8 bytes, we should get this as an info leak, which will contain the address of where the main pwnshop binary is located in memory. So cool. Yep, last pass. So that is our first exploit. So for step 2, we're going to do a libc leak. And we're going to do this by ropping, but ropping with a twist. We're also going to be doing a stack pivot. So we've done this rot payload before. Basically, we're just going to print out the address of a variable in the global offset table. The global offset table is just a mapping from function to address. So as the binary imports uses a bunch of external libraries, specifically libc, it doesn't know where they exist. So the global offset table is just a way to store those addresses. There's a little bit more to it, but that's the gist of what it does. So in the global offset table, there's going to be an entry for read, and it's going to have the value like OX7F, I don't know, 50, 60, 80, 31. I know I'm just making up values, but this could be an entry for read. And so if we could leak this value, we would then be able, and we knew what type of libc it was using, we'd then be able to calculate the base of libc, and once we use that, we can eventually jump to system. So a payload to do this would look like this. So first, I'm not sure how I'm going to align this. So we're going to say this side is the stack, and this is the text segment. So if non-executable stack was disabled, if it wasn't enabled, we would be able to just inject shellcode directly into the process, and we would then be able to execute it. But since we're not able to inject shellcode, we have to reuse existing gadgets that already exist within the binary. And there's a couple of interesting ones. So somewhere in the text segment, like the instruction segment within the binary, there is a gadget that does pop, RDI, and then it does ret. So that is one of our gadgets. And let's actually put the data section down here. And we're going to say read OX, what do we say, 7F, 50, 60, 70, 81, something like that. So cool. We're going to send a stack payload that first, what it's going to do is it's going to contain the address to this gadget. We're going to put it right here. In our second payload, we are going to put the address of this read thing right here. Cool. In the third, there's another segment called the PLT, and it's going to have a address such that when you call that address, it'll eventually call puts. And we're going to put that here. And then for the last gadget, we're going to go back to also in the text segment, there is that buy function. I'm just going to call it buy. That does, the whole chain load, like, how much are you offering, blah, blah, blah. We're going to put that here. So a little bit confusing. We're grabbing stuff from all over the place. But what's going to happen first is we're going to send this. It's going to be a little bit more complex. We're going to add another layer of complexity in a second. We're just going to imagine we're doing a normal ROP payload. First, what's going to happen is the stack is going to be pointing right here, and it's going to pop off this value and set it to RIP. And so RIP is going to start executing here. So RIP is then going to pop RDI and return. So when it pops RDI, it's going to read the next value on the stack, which is this address here, which currently contains this address to this. So we want to figure out what this value is. So we're putting that address here. So now RDI has the value for the global offset table entry for read. Then it's going to return, and it's going to start executing here. So execution is going to jump from this place, which is the call to puts. So at this point, puts is going to be called, and its RDI is currently this value, or this address. And so puts is going to print out this address. Once puts is done, it's going to return, and the stack pointer is going to be down here, and it's going to execute whatever in this address, and we put in the function for buy. So after what all this code is going to do is it's going to print out our libc address, and it's going to jump back to normal-ish execution. So what makes this stack pivot somewhat interesting is that we don't get to write that much data. We have a very limited write, and so we have to do the stack pivot. And so what's happening is we get to read into inbuff. And let's say all the way down here is the RIP that's going to be popped off the stack and set into RIP. We only get to write to here. So we do get to overwrite RIP, but what's common in a lot of these ROP challenges is you get to continue writing, and so you would put your ROP payload, after RIP, because it's going to execute whatever is here, then it's going to pop off, and it's going to execute there, and it's going to go off the screen. But we don't get that. It stops execution right here, so we get a single jump. So we get to do one thing, and that's it. And then it's going to continue and jump back to libc or whatever it's going after that. But thankfully, there was a very interesting gadget in this binary. So back to the text segment, there was a gadget that I think it was sub RSP OX28, and then ret. So what we're going to do is we're going to set RIP equal to this gadget, this sub RSP OX28. So at the very end of the function, RSP is right here. It's going to pop this value off, set it to RIP. It's going to start, so RSP is going to be down here somewhere now. Who knows where. RIP is going to be right here. RIP is going to execute this sub RSP. So now RSP is going to come all the way back up here. So, somewhere minus OX28, whatever that bytes is. And then, it's going to execute the return. And so RSP is now going to pop off whatever is right here. So this is exactly the gadget we need. Instead of putting our ROP payload afterwards, we're actually just going to put our ROP payload before. This is just one gadget that happened to be there. There's others, like sometimes you can get an exchange gadget where you can swap RSP with another gadget, with another register. There's move. Maybe you'll get lucky and there'll be a move instruction where you can assign a specific variable to RSP. You can also use leave. Ret is another stack pivot gadget. These are the things you would look for. There was also a pop RSP gadget in this binary. It's a little bit difficult to use pop RSP because you would need more space after here to actually do that popping, and we don't have that. But there's a bunch of different ways. Basically, when we do a stack pivot, all we're doing is we're just kind of moving the stack somewhere else. In this case, we had a beautiful gadget, this RSP minus 28. And so we can just move it here and then start executing our buffer, our ROP code here. But that's pretty much all a stack pivot is. But anyways, so we have a stack pivot. So that just means we're going to put our ROP payload first. And then at the very end of our ROP payload, where the RIP is going to be normally on the stack, we're just going to put this ROP gadget. So that's how I do that. And that's how we're going to get our libc leak. We're then just going to use the exact same technique. So 3, this time we're going to call system. I'm just going to say system, and obviously we don't need this anymore. So instead, now that we have the address for libc, somewhere in libc there's the string bin shell. So we're going to use our pop RDI gadget again, we're going to load in bin shell into RDI, and then we're just going to jump directly to wherever system is within libc, like we would call it normally. And from that point on, it should just call bin shell. Like I said, we have to do the stack pivot again. So again, we're going to use that sub gadget. So what was it, like sub RSP OX28. We're still going to use that gadget, put it into RSP to use it with our IP. And so that way the stack pointer jumps back up here and then we execute it, but otherwise it's the exact same thing. And yeah, after that we should just get shell. So let's look at the solution. Clear that. And where's my code? Cool. Like I said, there's two different solutions. There's one that works locally and there's one that works remote. And that is because we weren't given the libc that the remote challenge is using. We have to leak that. And I'll talk about that. We're going to cover the local solution, get that working, and then I'm going to show how you can leak the remote libc and how we can use that. But anyways, this is the solve script, standard sort of stuff here. We're going to import pwn, time, warnings, and disable warnings. We load in the elf, we set the context. This helps pwn tools do a bunch of clever stuff in the back, like 64-bit, we set the architecture, all that stuff. We have logging enabled. I use tmux because I'm in Docker, and so it just makes it so the panels are side by side. We're using my local libc, so this is the libc that the Docker is using. Again, not the same libc that is being used on the remote process. So step one is leak the elf address. So if we open up the binary again, so let's make Ubuntu, and it's called pwnshop. Let me move this over a little bit. So we're sending 2. Let me move this. We're going to send A2, and then it says after cell, we're just hitting a new line, and then after that, we're going to send 8 A's. So 1, 2, 3, 4, 5, 6, 7, 8. Like I said, we're filling up that buffer, and so that print %s should just continue printing more interesting stuff. And we can see we get this random garbage here. And this is our info leak for the main elf binary. So then we just receive up until this point. I'm going to receive 6 bytes, which I do here. And then I calculate the offset. To do this, I'll show how to do it for libc in a second, but you've seen these, if you've seen any of my videos, we do it in all of our videos. You just do a VM map, you calculate the difference between the leak and the VM map, and you know that offset will always be the same every single time. And then we print it out. Step 2, we need to calculate the stack overflow offset. So we're going to start doing the stack pivot, but first we need to figure out how far of an overflow we have to do before we're at that RIP. And so to do that, I think I have it all set up. Oh, I do have it all set up. Cool. We're going to attach GDB. We're going to go to this one. So we're going to do a buy, and then we're going to send a pwn cyclic. So it's going to be 100 bytes of like AAA, BAA, CAA, DAA, blah, blah, blah. And that way we'll be able to calculate that offset. Python tmux, Python 3 solve. I should make this bigger. Cool. Let's just make this full screen. And we're going to hit continue, and something breaks, which is exactly what we want. So we sent this giant string, and it's only reading like 40 or 60 bytes, something in that realm. But we can see it errored out here. We can't see the error because the text is too big. But basically, we can see on RSP, it's mad because it was trying to return to this. And specifically, it was trying to return to this address, which doesn't make any sense. Like, this is not a valid address. So we know that our buffer overflow really starts right here, SAAA. So we copy that out. And that is our offset that we're going to use. So all this code basically, all it does is it just calculates the offset where our buffer overflow really starts. And from here, we can start ropping. So this is how we generate the ROP payload. We're going to use pwnROP. It's absolutely amazing. So we're saying ROP call puts. So it's using that PLT call on the address of elf got puts. So like I said, amazing stuff. Basically, this is going to do our pop RDI gadget for us. It's going to figure out what that is. Oh, I think in the demo whiteboard, I was doing read. Here I'm doing puts. Doesn't make a difference. We can do actually, if we want to do read, we just put read here and we put read here. But we're going to read that read section on the got. The read entry on the got. We're going to print it out. Then we're going to jump back to the buy function. Oops. This is the code that's going to be set on the RIP that is returned. So this is all ROP code. And then here I'm just inserting the address. I didn't really need to do this. Really, I could pull this out. It's probably actually cleaner to pull it out. Actually, let's just do that. So we're going to, actually, no, I can't because I'm doing a -8 here. But yeah, this is just going to be what our RIP eventually jumps to. And that's the sub RSP OX28. Oh, and to calculate that value, there's a really handy tool called Ropper. So you go here, and it was called pwnshop. And we can see all the gadgets that are here. We want ones that involve grep RSP. So we can look here, and here is a sub RSP28. So at this offset within the main binary, we have our interesting little gadget. Like I said, there was a pop RSP gadget right here, which is also pretty interesting, but we would have to, we don't get enough, we have to be able to insert a value after the RIP on the stack, and we just don't get that. If there was a leave gadget too, I'd also check that out, but I didn't see one. Cool. So yeah, we send that payload off, and it should just print out libc. And then at that point, we're just going to build another ROP payload, do the same thing, and yeah, pretty much the same. Here we had there was some stack alignment issue. So on this local machine, I'm using a newer version of libc, and because of that, when you call into libc functions, it uses some like XMMO sort of functions that require things to be 16-bit aligned or 16 value aligned. And so because of that, sometimes you just have to insert an extra return statement in there. So all this code really is just return. It doesn't do anything special. Then we're going to do ROP system. We're going to say call system on the string bin shell. So this is going to search for bin shell within libc. And then it's going to do the RDI gadget, load it into system, and then yeah, we should get shell. And again, we're doing the same thing. We have to do that pivot. So this is the thing that's going to overwrite the RIP on the stack. So this will be executed, then RSP will be subtracted by 28. So then it'll jump here, and it'll execute the return, and then the pop RDI with bin shell, and then system. Yeah, from that we should just get shell. Python 3 solve.py. Sweet. And we can see we are root. So pretty cool. So to figure out what version of libc the remote system is using, we can use a pretty clever trick and a very nifty tool, this libc database search tool, to figure it out. So as a demo, let's first figure out what version of libc I'm using on my local machine, even though we already know what it is, just as good practice. And so to do that, we need to calculate or figure out what the last 3 nibbles of some leaked address are. And that'll actually, if we do a couple of those, that'll be enough information to figure out what libc version is being used, which is pretty crazy. And so the way this works is, I'm jumping into GDB, I'm hitting run, then I'm going to vnmap. So when libc is loaded, the last 3 nibbles are always 0, 0, 0. And so somewhere in here, let's say we're printing out read. Read will always end in this, FCO, for this specific version of libc. These values are going to shift up and down, as libc is loaded in different places, but this FCO will always be constant. Cool, for this version of libc. And so what we can take this, we'll put this here, and we're going to say this is the read function. Oops, we're going to remove this, and we say find. And so it is saying we are using one of these. I'm using this one, libc 6, because I'm on Ubuntu. If this wasn't enough information, like maybe there's still a whole bunch of different versions, all we have to do is leak out a different entry. So right now we're leaking read, but we can leak puts, and let's also calculate puts here. Normally, I mean, we just printed out puts, but actually let's go and run the binary. We're going to leak out the value for puts, and so we can see this was our libc leak. So the puts address is 420. Hell yeah. So we're going to 420 it up in here. And there we go. It has correctly determined the version of libc. So now we just need to do this on the remote binary. To do that, we have a remote script. It's loading in this remote, so we're not going to be using process anymore. And we are going to print out the address of read. So let's do that. Python 3 remote. Here, actually, let me clear screen. Python 3 remote solve. So obviously everything's going to be wrong. Like this is not the base of libc, and it should crash, which is fine. But here is the value of read. So we're going to add that. Read that. Let's do find. We have a couple different versions, so it's either Ubuntu, it's either 223 or one of these. Let's print out another address. So read. Let's see if puts is still 420. It won't be, but you never know. Python 3 remote solve. So let's leak out the address for puts. So puts is at 6AO. We'll do a find. And here we go. We have found our libc. So we can click on this. This tool gives you a nice little way to calculate the offsets between everything. Since we're using pwntool, it's easy just to download it. You can see I already have it downloaded here, but we'll copy out. We'll exit out everything. We're gonna move from downloads, it was libc, to here. We're gonna copy this. So this is the libc that's being used on the remote system. And all we really need it for is calculating offsets. So instead of using this libc, which is from the binary, we're going to use pwn.elf, this one. And so now when we calculate offsets, it'll be using the correct libc for our exploit. Cool. And from there, like, if everything worked, it should have just worked. We don't have GDB in here. Nope. So let's go back into the Ubuntu box. Python 3. We want remote solve. Remote solve, that's using the correct version of libc. Boom, boom, boom. It's loading gadgets. A little slow, but we can see our libc address ends in 000, which is exactly what we want. So if it ends in 00, it's probably good. And we do an ls, and we have flag, so we can cut out the flag. Or sorry, we have shell. And here's the flag. This is what I call a good deal. So, like I said, very fun challenge. It was very cool. We got to do some stack pivots. We got to figure out, a remote version of libc. It was a good info leak using the %n. So all in all, very fun challenge. And I'll see you at the next write-up. Cheers.